everyone, and welcome to section 3.9. So I did double check the syllabus just to make sure, but we do not do 3.8. So if you're looking for 3.8, because it's not there, it's because we don't cover it. So I just wanted to double check with the syllabus to make sure that was the thing. And it is the thing, so we're jumping right into 3.9. We're going to talk about related rates, which means we're going to use a lot of implicit differentiation throughout this section. We're talking about word problems, but word problems that require some calculus in order to solve. So let's just take, for example, let's say we have like a linear measurement. Let's say we have like a ruler that has length L. Now I know a ruler is still two-dimensional, but think about it in terms of just a linear measurement length. If I want to take this and double the length, it's not a terribly hard process, right? There's one length, there's two lengths. The whole thing has length 2L. So if I double the length, I just simply double what I already had. But this is for linear measurements. If we start getting into things that are a little bit more involved as far as like two-dimensional objects, let's say we're in 2D space, and we have, let's just take like a sheet of cardboard or something like that, whose length is twice the width. So we can mark it down as having width W, and then its length is twice the width. Now we're talking about something that's two-dimensional, and I can start calculating its area. And in this case, the area is just going to be the length times the width. Well, the length is 2W times another W. That's 2W squared. So here, if I doubled the length, I just multiplied by 2, right? Simple. But what if I want to double the width here? Well, I end up doubling the size of this entire rectangle. I don't simply double the area. You can see that I've done a lot more to the area. Right? So if I want double this size of this original rectangle, I have to think about what am I doubling? I'm only doubling the width to get 2W, but it's affecting my area a lot more than just a simple multiple of 2. Now my area is going to be, when I look at it, the length times the width. Well, my length is going to be 4W, and my width is going to be 2W. 4W times 2W is 8W squared. Right, so you can see it made a bigger difference than just simply doubling my original area. I'm missing something else, right? And of course, this extends into three-dimensional space. Right, so you have like a cube, some sort of like box, and they all have length, sides. We'll just call it S. Then we start talking about volume, and in this case, the volume will be S cubed. Well, what if I want to make this box 3 times as large? I can't simply multiply the volume by 3, because if I affect one side by 3, mainly like the width, then I also affect the length by 3 and the height by 3, because I still want to maintain that cube shape. So if I go tripling one of the sides, I actually end up tripling every measurement. Well, now I've got 3S times 3S times 3S. That means my volume is now 3S quantity cubed, which is 27S cubed. So you can see that when you get into these types of problems that require a little bit more than just linear measurements, you have to be very careful. As you change one of the sides, you're also inherently relating that other side to a certain change, right? So as you double this side and double this side, you're not just doubling the area. Right? You can see there's a lot more involved. So the rate at which you change the width is related somehow to the rate at which the area changes. the rate at which you change the length of one of these sides is related to the volume. So our goal is to find those relationships. And of course, since they are rates of change, how fast am I increasing that area? How fast am I increasing that volume? Those are rates of change, and that's all explained through the derivative. So that'll be the goal for this whole section, really, is just, a bunch of word problems that allow you to use the calculus to relate these changes. That way we're not just stuck in this kind of boring linear world anymore. So in the real world, there's a lot more involved. If I'm inflating a balloon and the radius of that balloon is growing at, say like an inch every 5 seconds, it doesn't mean the volume is growing at an inch every 5 seconds. That doesn't make sense. Volume is cubic, right? It's not linear. It's not a linear measurement. So you have to relate one of these linear measurements to one of these cubic measurements. Again, all through calculus. So I've got a couple problems pulled up on the desktop here. See if I can make that visual. There we go. Just starting out with a couple of the homework problems. Well, I guess not really homework if you're only doing the odd, but just starting out with a couple of the basic homework problems. And number 4 says that the length of a rectangle is increasing at a rate of 8 centimeters per second, and its width is increasing at a rate of 3 centimeters per second. When the length is 20 centimeters and the width is 10 centimeters, how fast is the area of the rectangle increasing? So we saw, again, we can't just simply take some of those numbers and multiply by, say, double it or triple it and be done with it. That's not going to work for us. We've got to take into account the relationship between width and length and the area as that change is affected. So let's jot it down. I say for any word problem, you always want to try and at least draw a picture to get your head wrapped around it. It doesn't have to be a pretty picture. There's a rectangle. The length of the rectangle is increasing at a rate, there's that word rate, 8 centimeters per second. So the length has a rate of change, and it's in centimeters per second. So it's a length measurement in centimeters. And I'm going to use dt for the change in the length over the change in time. So I'm using t as time because we're talking about change per second. And that was 8 centimeters per second. All right, so now I'm just jotting down what the book tells me. I'm taking all my givens and I'm just getting them down. It also mentions that the width is increasing at a rate of 3 centimeters per second. The change in the width with respect to time is 3 centimeters per second. Then it wants to know when the length is 20 centimeters and the width is 10 centimeters. Those are just straightforward linear measurements. How fast is the area of the rectangle increasing? So these are all the things that they tell me that I know. They say, make sure you take all this stuff and relate it to the area. So I need the formula for the area first, right? If I don't have an area formula, then I can't talk about change in area. So I better get an area formula first. I'm going to use capital A. Since we're talking about areas length times width, or you can do width times length. However you do it, doesn't matter. It's commutative. So if this is my area, I could simply plug in W and L and tell you the area. But that's not all that's happening. They want to know how fast the area is changing. They want to know the change in the area with respect to time. And again, this is why notation is so important. If you don't write this, then no one knows what you're doing. You have to make sure you're writing the notation out so you know what to do. You could call these L prime, W prime, A prime, but I like the T because it's telling us it's with respect to time. Not everything is always going to be with respect to time. So it helps us keep track of the units a little better. So I'm taking my area formula and I'm differentiating it, which means I differentiate the left and I differentiate the right but both L and W are varying, right? And they're not the same. This isn't W and 2W, so it's not like I can rewrite everything in terms of one variable. I have to use a product rule. And that product rule says both of these are varying. They're both variables. So when I take their product and I differentiate it, I get the derivative of the first times the second plus the first times the derivative of the second. Right, so they never gave me a relationship between W and L. I know it looks like here, yeah, that's just L is twice W, but I'm going to do the entire formula written out because I need to keep track of dL dt and dW dt because they're changing at different rates. So now I have all my pieces that the problem told me, and I have my formula for area now differentiated so it tells me the change in the area with respect to time. So I can plug in the rate of change for the length times my width, plus I can plug in my length times the rate of change for the width. So that means dA dt is going to be 80 plus, sorry, not 40, 60, which tells me that the rate of change of the area with respect to time is 140, and we were dealing with centimeters per second. And that's the other important thing is those units need to make sense. You don't want to say the change in area with respect to time is 140 seconds. It doesn't make sense. You're changing a physical unit with respect to a actual timestamp. So you want to make sure you get the proper units there. Oh, I say that, and then I forgot my. All right, we're talking about change in area. So it's square centimeters. So you can see there's just some calculus involved to relate all these rates to some other rate. In this case, it was the change in area. So that's a pretty straightforward problem as far as key elements here. Again, one, oops, guess blue's done. One, draw a picture. Pictures always help. If you get a good picture going, that'll really help you at least attempt the problem. Then you have your givens, right? Jot down what's been given to you. That way you're not trying to hold all this information in your brain while your brain is trying to solve the problem. Get it down on paper, that way you can clear your headspace and just work the problem out. You can always go back and reference the things that you need to. Sometimes word problems are a bit too wordy, and it's nicer to just make a list of givens. You're always going to need some sort of area or volume or some formula. You're going to need a formula so that you can differentiate that formula to start talking about the rates of change. It just has to happen. Right? And then when you do differentiate, right, make sure you're taking the time to differentiate properly. This one also really did need some implicit differentiation because I don't know what L is, but I know it's a function of time because it's changing with respect to the variable time. So you may need to use the right differentiation techniques. Right, and then once you've got that, basically, now you're on the home stretch, right? You're just plugging in all your knowns, whatever you've been given, you're plugging those things in, and now you're actually computing. This is when you actually start to, calculate the result. Right, you shouldn't really be doing any calculation before this part. Some people want to jump the gun and say, oh, okay, here's the area. Well, I'll just plug in 20 and 10, and it's 200, and I'm done. You never found change. You didn't do anything. You just found the straightforward area, which we did way back in algebra. Right? You never even mentioned change. So you're going to need the calculus to get there. So again, it's just kind of like a step-by-step. rough breakdown, they don't all behave exactly the same. That's why I wanted to pick a couple different examples. But as far as as far as related rates go, this is the gist of the problem-solving strategy, right? Get your head wrapped around a nice picture, get those givens down, grab the correct formula you need, differentiate that formula, that's the heart of the problem, then plug and chug. And I would say maybe last piece, number 6, don't forget your units on the end to make sense of the answer. No point in getting the correct number if the units don't make any sense at all, then it's just a bunch of gibberish. So not too terrible for the first one, and let's do the next one there. Since it's already on the screen, it says a cylindrical tank with radius 5 inches is being filled with water at a rate of 3 cubic meters per minute. How fast is the height of the water increasing? So again, we want to take a nice little picture. Here's a cylindrical tank. You can tell you do not have to be the best artist in the world. Right? You just got to get some sort of picture down. So it has, maybe I'll just do the top one, some sort of fixed radius. So here's my picture. And again, it says the radius is 5 meters. So that thing is fixed. That radius is not really going anywhere. So it's not that the radius is increasing or decreasing, it's the height of the tank. So we need a formula for that volume of the tank, since now we're in 3 dimensions. And the formula is going to be pi r squared, which is how we get our circle bit, times the height. So that'll be the volume for that right cylindrical tank. I say right because it's not like slanted or cantered, if you will. We also know that the water is increasing at a rate of 3 cubic meters per minute. So as we're filling this thing up, it's increasing at a rate of 3 cubic meters per minute. Those are cubic meters, so that's obviously the volume, not just some linear measurement like height. Okay, so I jotted down my givens, and now I can go for a strategy to solve the problem. Again, I needed that formula. So let's take this and differentiate it. dV dt is going to be pi is just a multiple, so it sits there. R, well, R is fixed, right? So it doesn't really matter that it gets differentiated. It really is just a fixed number. It's never going to change. It's always going to be 5. I'll just have to square it when I get to the formula. My variable, the thing that's varying, is the height. All right, this height is varying because my water level is rising. So sometimes you can go back and modify your picture to help you make a little more sense of it. Aha, H is changing. R is never changing. It's not varying. I don't differentiate it as a variable. It's just a constant multiple. Same thing with the pi. But I do have to differentiate the height with respect to time because it is a variable. So when I differentiate my formula, I'm differentiating with respect to t because h is a function of t. Volume is a function of t. It all depends on what time we are at. So properly using some implicit differentiation there. Now I can go and plug in what I have. dV dt on the left-hand side was actually told to us. We know the volume of the tank, the water inside, is increasing at a rate of 3 cubic meters per minute. Pi is always pi. There's nothing to change there. Radius is fixed at 5 meters, so that's 5 squared. Don't forget the square. The change in height with respect to time, that's the thing I don't know. That's the thing I have to solve. So this tells me that I have 3 is equal to 25 pi dH dt, and I can divide by 25 pi on both sides. And now I know that the change in height with respect to time is going to be 3 over 25 pi. And since it's change in height, I'm going to do meters per, since it's change in time, I'm going to do seconds. Remember that your units have to agree both on the left hand and the right hand side. Height per time, well, height we're talking about meters in this problem. Time we're talking about minutes, so I wrote seconds. Let's fix that. And yes, the original problem was in minutes. Good. So the height is increasing at this rate, 3 over 25 pi meters per minute. If you need to approximate that for something you're doing, because it's a, kind of a weird irrational number, then you can approximate it for whatever you're doing. But again, we want exact answers. Right? There's no reason to do all this good calculus and then say, it's about this. No, tell me what it is. That's the answer. Right? We're done. Why would you even bother picking up a calculator? Notice I didn't use a calculator there. But if it says to approximate, then we'll take the extra step. If not, then we don't. Okay. Maybe I can turn that book off for a second. And I'm going to pull one out of, well, I guess technically it's still out of the book, but it's just not too long of a problem. So I can rewrite it. Some of the problems in this section are a bit more, straightforward algebraic, I guess you might say. So here's one that says, suppose 4x squared plus 9y squared equals 36, where x and y are functions of t. And they want to say if dy dt is 1/3, find dx dt. When x is equal to 2 and y is equal to 2 root 5 over 3. So they're not really getting too much into like a real world application or anything like that. There's kind of no picture to draw because they're just handing you the function and telling you to work with it. So keep in mind always what you want to solve for, right? We really want to solve for dx dt. Now, x and y are both functions of time. So really, and we don't have to rewrite it like this, but really we have for x of t being squared plus 9y of t being squared. This is not a variable y. It is a function y. T is the variable. This is not a variable x being squared. It is a function x of the variable t being squared. All right, so this is really the true story here. It is not a variable x and y. X is a function of t. Y is a function of t. All right, so there are parameters that we have to adjust for. That's why we're not doing dy dx, right? Because x is not the variable of the function y. T is the variable of the function y. T is the variable of the function x. So we'll have to be a little more careful. Now, when I do differentiate it, I'm not going to keep rewriting x of t, y of t, because then there's just too many letters involved. So I will stick with their notation. But I just wanted to show you that you're not squaring variables, you're squaring functions. You're not squaring variables, you're squaring functions. But now when we go to differentiate, again, implicit differentiation. So I'm going to start with the left-hand side. 4 is a multiple. I differentiate x squared. I get 2x. But then because x is a function of the variable t, implicit differentiation says I just used chain rule, right? The 2 came down. I reduced the power by 1. Now I have to multiply by the derivative of the inner function, which is x of t. Plus 9. I differentiate this. I get, put a little dot there, 2y, but then I have to multiply by dy dt, thanks to chain rule. Derivative on the right is 0, because it's just a constant. So again, I'm differentiating a function. The square comes down. I reduce the power by 1, but then I multiply by the derivative of the inside x. Well, I don't know what the derivative of x is explicitly, so I have to do it implicitly. So I've got 8x dx dt plus 18y dy dt. Which means now I can start going and plugging in all these things that they told me. dy dt is a third, x has to be 2, and y has to be 2 root 5 over 3. So 8 times, I'm plugging in 2. Again, my goal is to find dx dt, so I'll isolate that later. Y is 2 root 5 over 3. dy dt was 1/3. Oh, forgot my equals 0 over there. Keep track of all that. See, can I go down? Well, let's move it up here. We're not going to need too much more space. So now we'll say 8 times 2, there is 16 dx dt. We've got 18 times 2 root 5 over 3. I'm going to simplify that because 3 goes into 18 6 times, so that's not too terrible. I'll just write 12 root 5. Well, I guess I could reduce again, right? Because 3 goes into 6 twice. So I guess I only have 4 root 5 sitting there. Okay, now we can solve for dx dt. First, we'll isolate that term by subtracting 4 root 5 on both sides, which will give us 16 dx dt is negative 4 root 5. And then we'll divide by that multiple of 16. Sorry, it looks like I just crossed out dt. I did not. There we go. Just divided by 16. Which gives us dx dt is equal to, and we'll reduce this to negative root 5 over 4. There's no unit to worry about here. Right? They never told us any sort of like real world measurement. So we're just going to leave the algebra as is, just a numerical result. The change in x with respect to t is negative root 5 over 4. So a little more straightforward, just a bunch of algebra, not really a picture you can draw there. The next one will have a picture. So again, you got to really hone in on these relations. Hopefully this one will be a really nice problem. This one says gravel is being dumped from a conveyor belt at a rate of 30 cubic feet per minute. Actually, this is number 29, which is technically a homework problem. So I'm just going to change that number to 40 cubic feet per minute. That way I'm not stealing your homework from you. And then you can go give 29 a try. So this is number 29 from the homework, except I did tweak this. So keep that in mind when you compare your answer. I'll let you do 29, and its coarseness. But I'll change it so it's a little different. It is such that it forms a pile in the shape of a cone whose base diameter is, whose base diameter and height are always equal. So that maintains the fact that if the height goes up, the base goes up, the base gets wide the same amount. And it wants us to know how fast is the height of the pile increasing when the pile is 10 feet high, aka when h is 10 feet. So again, we'll start with just a nice picture. There's a pile in the shape of a cone. Now they tell us that the height from the center of the pile straight up is the same as the base. Right, so those two are the same length always, no matter what. If I pour more sand or gravel on top and it grows larger, then this also grows, so that those measurements are exactly the same. The height and the base are always the same measurement. So we want to keep that in check. So first things first, when we look at this, let's write down that this is our change in volume. dV dt is equal to, and again, I changed this number from 30 to 40. Hopefully that doesn't break the problem. It shouldn't. I'm just dumping more gravel than the original problem is. So it's a little tweak there, but not too terrible. Then I have h is equal to 10. Well, I can't just plug that into the problem right away because it's not always 10, so I can't just say it's always 10. I'm going to have to work with my rates of change, and then I'll go back and say, okay, now I'll let h equal 10 to figure that out. But this h equals 10 is also the diameter of the base. So I'm going to mark that down because it says the base diameter and height are always equal. Now, diameter is d, but I'm going to use r because the formula is going to need r anyway. So the height is the same as the diameter, but the diameter is twice the radius. So that's why I'm saying those are going to be equal values. So now, we basically got all the information that was given. What we need is some sort of formula. Since it's a cone, and we're talking about change in volume as one of the givens, we're going to use that volume to our advantage. And the volume for a cone is going to be 1/3 pi r squared times the height h. So there's the volume for a right cone. Now if you look here, I've got two variables, my radius and my height, and they're both changing because as I pour more gravel on top and it grows higher, it must grow wider. So the rates of those are both going to be changing, so these are both varying. So what I'm going to do is I'm going to use this to my benefit. H is exactly 2r. Now before you go writing h as 2r and getting a volume in terms of only the radius, think about what you need in the end. Our goal is to look for how fast is the height of the pile increasing. So we need dh dt. How fast is the height of the pile increasing? So it makes no sense for me to like convert this in terms of all r's because I don't want dr dt at all. I want the change in the height, dh dt. So I'm going to do it the other way. I'm going to look at r as h over 2. And I'll do that instead, just because that relationship will leave everything in terms of h. Now I have my volume is 1/3 pi. Instead of r being squared, I'm going to have h over 2 being squared. All right, so using that relationship that they gave us where the base diameter and height are always equal, I can rewrite everything in terms of one variable, which, as we've already known, is a lot easier than dealing with two variables, which means my volume is going to be given by, if I square this out, I'll get h squared over 4. Then there's this 3 down here, and I'm multiplying by pi. So I'm going to rewrite that as pi over 12. Right? Pi is a multiple up top. 3 times 4 on the bottom is 12 on the bottom. And of course, h squared times h is h cubed. So I'm really just trying to simplify that formula down so that now I can differentiate it and it's not going to be too much of a pain in the butt. So let's do that. Let's differentiate it. dv dt, right? I'm differentiating volume with respect to time, right? Cubic feet per minute, is equal to, so I'm going to still have this pi over 12 multiple, but then h is a function of time, right? H is changing depending on my variable t, so h is a function. So I'm going to have to use chain rule. 3 comes down. H is my inner function that just gets copy and pasted, but I have to reduce the power by 1. Now chain rule says I have to multiply by the derivative of that inner function h of t. Well, that is h prime, aka dh dt. So I can reduce that just a little bit. And that 3 goes into 12 4 times. So dv dt is equal to pi over 4 times h squared times dh dt. Well, let's start plugging in what we got. We know that dv dt, that is the change in the volume with respect to time, is 40 cubic feet per minute. That must equal pi over 4 times h squared. Well, they told us when the height was 10. Now I can plug in that h at that specific moment. I want my height to be 10 feet at that time to get the proper change in height at that time. So overall, I've got 40 is 100 pi over 4 times dh dt. Then we'll multiply by the reciprocal over here. So I'm going to do 4 times 40, that's 160. Then I'm going to divide by 100 pi to get dh dt. Sorry for squeezing it in so low there. And I'll reduce that 160 over 100, 16 over 10, 8 over 5 pi. Back to our proper units, we're talking about change in height. So it is just feet per minute. Right? Height is just a linear measurement. But it is a rate, so I do need feet per minute. Again, no reason to approximate that. If they don't say to, I'm just going to leave it. So again, it's all about that relationship. Using the derivative to get the proper rate related. And again, typically it's going for a formula. You may need to look up a formula if you're unfamiliar with it. Clean all that up down there. And then let's take a look at, another thing I wanted to mention is if you look in the textbook and you go to, actually if I pull this up real quick, and maybe we'll drag this up a little further here, full screen it. If you look in the textbook and you go back to the examples, there are some really good examples in here. Obviously, I don't want to just simply copy and paste these examples. I wanted to work on some of my own, but you can see that there's formulas are kind of there for most of the problems that are typical of this section. Example 2 is really great. That ladder problem is awesome, about a ladder sliding down the wall. And you can follow these pretty nicely. Right, they're explained very well. Right, so look at those examples and work through them as well. Those are tons and tons of great examples. I'll just bottom that out and turn this off. Look at those examples. Those are great examples to work through to help you get started. Or if you're stuck in the middle of a problem, go back and see what they did in those examples to get them through. I want to look at one more. I'm just going to, again, steal from the textbook, but this will be me stealing from one of the, it's in like 48 in the textbook, so it's a little after the ones that we even need to do. But I just think it's a nice problem, but I do give it one little tweak. And it says, two people start from the same point. Don't worry, it won't be too much writing. It's not that wordy. One walks east. Don't need to capitalize that. At, let's see what they give us, 3 miles per hour. And the other walks north at 2 miles per hour. And it wants us to know how fast is the distance between people changing after $15 minutes. First thing to note, really careful here. They told us that their rates at which they're walking, one of them's going east at 3 miles per hour. I'm just going to put them here and say there's their rate, 3 miles per hour. And then the other one walking north at 2 miles per hour. And maybe they're not going as fast, so I'll put them here and say that they go 2 miles per hour. And then they tell you after 15 minutes. Right? So they're mixing up these units. These are in terms of hours. You're differentiating with respect to hours, right? Miles per hour, miles per hour. All your rates here are in terms of hours, and this is in terms of minutes. 15 minutes is not 15 hours. 15 minutes is a fourth of an hour. Right? So do be very careful about that. 9 times out of 10, the textbook isn't trying to be that tricky, but in this case, this is one of those like, haha, gotcha moments. You wrote 15 for 15 hours instead of 0.25 or a quarter of an hour. All right, so do keep that in mind. Sometimes when you read through the problem, they might mix some units up. They might give you this thing in terms of centimeters and then this in terms of meters. Well, you can't correlate those directly in one formula like centimeters and meters. You're going to have to convert one or the other. So keep that in mind. The other thing that they want is they want to know this distance, how fast that distance is increasing. So you can see as these guys start walking, one walks faster than the other, that distance is not just going to double and triple. If this guy's walking faster, that distance is going to kind of stretch out. So we need to relate these rates together. Okay, well, first things first, we're looking at a nice right triangle, so keep that in mind. And I'm just going to label these sides sort of typical like X, Y, and Z. You could do A, B, and C if you like. But this will help me get a relationship or some sort of formula that I can use. In that case, that formula is going to be X squared plus Y squared is Z squared. So that allows me to use that nice formula. Now I want to relate the rates, so I'm going to have to differentiate this. But again, X is a function of time. That distance is a function of time. Y is a function of time. Z is a function of time. So this isn't a variable X. It is a function, X of t, Y of t, Z of t. So these are functions, meaning there's a function inside a square function. Chain rule is going to have to apply. So I'll differentiate 2x to the first, but then I need dx dt for chain. Plus, I'll differentiate 2y to the first power, but then I need dy dt chain rule. Equals, again, 2z is a function of t, so I need dz dt, again, chain rule. One thing we could do to simplify the process at this point is the left is all multiplied by 2, common factor. The right is multiplied by 2. We could divide both sides by 2 and clean this up pretty quickly. All right, if I factor out the 2 and then divide both sides by 2, I can get that to look a little nicer. So what we need is things to plug into this formula. So far, we have, I'm going to list them off to the side here. So far, we have dx dt, right, the rate of change with respect to time for the x coordinate is 3. We have dy dt, right, this other person walking up has a rate of change of 2 miles per hour. But what we need to know is what to do with this 15 minutes, aka 1/4 of an hour. All right, so what we need to do is after 15 minutes, how fast is that distance increasing? Well, then we need to know where these people are at 15 minutes. Meaning I need to go back to my formula and see how far away these people are. So in terms of x, if I'm walking at 3 miles in 1 hour, I need 1/4 of that to see what my x is. So x is going to be, I do 3 miles in 1 hour, so I have to divide that by 4. So I get 3/4. Same thing for y. I go 2 miles an hour, but I want to know 1/4 of that because I haven't done the full hour. I've only done 15 minutes. So 2 miles needs to be chopped into 1/4 to get my 15 minutes. I go 1/2 of a mile. So this gives us our x and our y component that we need. But you'll notice the thing we're trying to solve for is the change in the distance, dz dt. Okay, I have x, I have y, I have dx dt, I have dy dt. I need to find dz dt, but I don't know z. All right, so I can plug in, plug in, plug in, plug in. Aha, I can't plug this in to solve this unknown. I'll still have an unknown. So I need to go back and figure out what z is. And I need that distance z to line up with these two distances at that 15-minute mark. So what I need to do is look at this triangle where x is 3/4 At 15 minutes, that's how far I've gone. And y is 1/2. Again, at 15 minutes, that's how far I've gone. And I can get the distance z at 15 minutes, that's how far I've gone. And then I'll show what that rate is at that 15 minutes. So if I look at this, it's going to be 1/2 squared plus 3/4 squared is equal to z squared. So I'm going to have to take the positive square root. Again, just simple Pythagorean theorem there. So I get the square root of, this is 1/4 plus 9/16. Common denominator, that'll be 13 over 16, all under the radical, is z. I'm simply going to take the square root of the denominator just to make it a little nicer. Root 13 over 4. Now I have all my components. Z gets plugged in, my y gets plugged in, my x gets plugged in, dx dt gets plugged in, dy dt gets plugged in. Everything can now be plugged into the formula. 1, 2, 3, 4, 5 spots, that's what I need. And then the remaining spot is just this dz dt. Okay, so let's isolate that and plug in everything. We now have x, which is 3/4. We now have dx dt, which is 3. And again, I just simplified it because everything was multiplied by 2. I got rid of those multiples of 2. We have, y is over here, 1/2. And then dy is this guy over here, 2. We have our z, root 13 over 4. And our goal is to isolate dz dt. So we'll just have to multiply by the reciprocal there. So we've got 9/4 plus 1. That's like 9/4 plus 4/4. That's 13/4. Is equal to root 13 over 4 dz dt. So then I'm going to multiply both sides by the reciprocal to get it to cancel out on the right-hand side. This will give me 4 over root 13 times 13 over 4 is dz dt. And make sure that screen is still showing that corner. Yeah, it's not bad. And then 13 divided by root 13, well, that's just going to leave me with root 13. So I'm going to do radical 13, and that is the change in distance with respect to time, where our distance was in miles and our time was in hours. So at 15 minutes, that distance between these two is increasing at a rate of radical 13 miles per hour at that 15-minute mark. And so again, just kind of really going back and relying on the old Pythagorean theorem. Now, I did say I tweaked this problem a little bit. It's like 48 in the book, but if you read the one 48 in the textbook, you'll notice a change in this word, and that really makes the problem a bit trickier, and that's kind of why we maybe don't go that far. I don't know. It's not that tricky. It just requires a little bit of law cosines, so it's not too terrible. But yeah, so that's it for 3.9 related rates. Every problem is going to feel a little bit different because it is a word problem. So every time, think about that strategy that I gave you, right? Draw a picture, write down those givens, write down those known quantities that they tell you within the word problem itself, right? Find a formula. There's got to be a formula that you need to use, be it area or volume or something like that, right? There's going to be some sort of formula that you have to grab. Differentiating that formula properly is really the heart of the problem. Making sure you get all your proper rates in the right spot. Use chain rule, use implicit differentiation, right? That's like the heart of the problem. And then you can finally go back and start plugging in things. You'll notice here we needed to go hunt down z, so that gave us like a little extra step we had to do off to the side. We really had to go hunt down that proper z and then return to our rates to make sure we didn't get stuck with a z and a dz dt and not be able to figure those out. So again, no 3.8 And that takes care of 3.9. And then 3.10 and 3.11, not too terrible, pretty short and sweet, so we'll get to those next, and then we'll be ready for exam 2. And yeah, we'll talk about that when we get there. So, thank you very much.